Alright, let's look at quantity of heat. Heat as energy. So we are trying to understand the concept of heat. Heat serving as an energy. Because generally, heat is an energy, okay? It's a type of energy, heat energy. So what is heat energy? Heat is a form of energy transferred due to temperature difference. So heat is a form of energy transferred due to what? Temperature difference. When we say transferred due to temperature difference, it means that when a body, if you bring two bodies close, when this body is hotter than this body, the hotter body has greater energy and more molecular mobility than the less hot body. So it's going to force heat into the less hot body if you bring the two bodies in contact, okay? So that's the transfer of heat energy according to temperature difference. It all depends on the body that has more energy, the body that has more molecular mobility. That's what's going to determine the direction of heat transfer. So heat transfers from the hotter to the cold body, or from the hotter to the less hot body, just like that. And likewise, there can also be exchange of heat, okay? So as it's transferring heat energy to the less hot body, if the less hot body was cold, okay? So since it's a less hot body, if we are talking about cold body now, you bring cold body and hot body together, there is going to be an exchange of heat and cold between the two bodies, just like that. There's going to be transfer of heat until a balance is stricken between the two bodies, okay? Giving the two bodies the same temperature, the same what? Temperature. So let's look at heat capacity. See, this is the symbol for heat capacity. And what is heat capacity? Heat capacity is the amount of heat required to raise the temperature of a body by 1 Kelvin. Mark the definition. The amount of heat required to raise the temperature of a body by 1 Kelvin. That's what? Heat capacity. And the expression of heat capacity, the formula is C, which is heat capacity, is equal to Q, okay, which is quantity of heat over change in what? Temperature. Specific heat capacity, small letter c. So heat capacity is capital letter C. But specific heat capacity is what? Small letter c. So specific heat capacity is the what? The heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. So in specific heat capacity, you have 1 kilogram, raising 1 kilogram. That's why it's specific. It's specific to 1 kilogram. The amount of heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. But heat capacity is just the amount of heat required to raise the temperature of a body by 1 Kelvin. But when it's specific, 1 kilogram is involved. Is the amount of heat required to raise 1 kilogram of a body, the temperature of 1 kilogram of a body by 1 Kelvin. And the expression of specific heat capacity is the quantity of heat is equal to MC times the change in what? Temperature. Where the temperature is the first step, where the temperature is the final temperature minus the initial temperature. Methods of determining heat capacity and specific heat capacity. What are the methods of determining heat capacity and specific heat capacity? The first one we have here is method of mixture, okay? And in this method of mixture, what do we do? Mix hot and cold substance together, just like I explained at first. When you mix a hot and a cold substance together, apply principle of conservation of energy. What is the principle of conservation of energy? The principle of conservation of energy that states that energy can neither be created nor destroyed, but can be transformed from one form to another. So when you bring a mixture, a hot mixture and a cold mixture, there is going to be transfer of both heat and cold, okay? So energy is not going to be created, energy is not going to be destroyed, but it's going to be transformed, it's going to be transferred, okay? So the next one we have here is electrical method. And what is the electrical method? Use electrical heater. Q, you know, the specific heat capacity is equal to I square ROT. This is the formula of electricity, okay? This ancient formula of electricity. Very, very easy. If you want to use, you can use this formula to arrive at various answers when it comes to electricity, okay? All you need to do is make what you are looking for the subject of the formula. So Q is equal to the quantity. So Q is equal to the quantity R. So Q is equal to the quantity I squared, which is what? The current squared, okay? Then R, which is the resistance, times what? T, which is the time. Then the third one is what? The Newton's law of cooling. And the Newton's law of the cooling goes this way. The rate of heat loss is directly proportional to the temperature difference between the body and the what? The surroundings. So the rate of heat loss is directly proportional to the difference between the body and the what? The surrounding. So that difference in temperature between the body and surrounding is equal to the rate of heat loss. So you can see that the ambient, the temperature between this body and the surrounding determines the rate of heat loss. So that's why when the weather is hot, you start sweating, it determines the rate at which you lose heat to the surroundings. Change of state. And what does change of state imply? It means when a substance changes, okay? It changes from one form to another, from one state to another, okay? So let's understand what the change of state implies. The first we have there is the latent heat. And what is latent heat? Capital letter L, only capital letter L. Latent heat is the heat absorbed or released during change of state without temperature change. So there's no temperature change during what? The latent heat. No temperature change. The heat absorbed or released, heat absorbed or evolved. It's just like the chemical reaction now. The heat absorbed or evolved during change of state That's when a reaction is occurring, or when a substance changes its state or its form. Okay, changing of states. Maybe you boil water, or you melt ice. Okay, so the latent heat is the heat absorbed or released during change of state without temperature change. So it's just like when ice melts, the heat absorbed or evolved when ice melts is an example of the latent heat, because without a temperature change is not involved. Okay, so that's that for that. Specific heat of fusion, LF. And what is specific heat of fusion? It is the heat required to convert 1 kilogram. Remember, anywhere you hear specific, just know that 1 kilogram is involved. Specific latent heat of fusion is the heat required to convert 1 kilogram of solid to liquid at what? Constant temperature. So here, we need constant temperature, okay, to convert 1 kilogram of solid to liquid. So the heat required to convert 1 kilogram of a substance from solid towards liquid, that's from solid towards to melting, okay, from solid to melting point, is the specific latent heat of fusion, okay. So let's look at specific latent heat of vaporization. And what is it? Is the heat required to convert 1 kilogram of liquid to gas at room temperature. So just know that latent heat of fusion, the specific latent heat of fusion, where you have fusion, just know that is the one that moves a substance from what? A solid then to what? Liquid. That's melting point. Then specific latent heat of vaporization is the heat required to convert 1 kilogram of a substance from liquid to gas. So from liquid to gas, latent heat of vaporization. Then from what? From solid to what? Liquid. That's melting point. Okay. Then from liquid to gas, that's boiling or evaporation. The next is melting. And what is melting? Solid turns liquid at melting point. That is the what? The simplest definition of melting. The next concept we have here is evaporation. And what is evaporation? Is the slow change from liquid to gas at surface, okay, below boiling point. So evaporation does not need boiling to occur, and it's what? Below surface. It does not involve the entire surface of the liquid. So that's the difference between boiling and evaporation, okay. Evaporation does not, it occurs below surface. It does not involve the whole surface of the liquid, okay. So it's the slow change, okay, from liquid to gas, okay, below boiling point. So much heat is not required to induce evaporation, and it does not involve every part of the liquid. So what is boiling? Boiling is the rapid change from liquid towards gas, okay, throughout liquid at what? Boiling point. So boiling occurs throughout the what? The liquid. Throughout. Every part of the liquid is associated with boiling. Every part of the liquid is part of what? Boiling. And it happens at what? Boiling point. Remember, it is a rapid change from what? From liquid to gas, okay. But evaporation is a slow change from liquid to gas, okay. In evaporation, the liquid is not required to get to boiling point for evaporation to occur. All right, so spot the difference, because Jamb usually repeats this question almost every year. So what is the effect of pressure / dissolved substances? What is the effect of pressure / dissolved substances? Number one, increased pressure raises boiling point. Yes, when the pressure is high, it gives the molecules of the liquid more viability, more power to move, more energy to move, more energy to bombard, okay, bombard the liquid container, and everywhere there is more collision, okay, between the molecules of the liquid because of high pressure. So increased pressure raises boiling point. So when there's high pressure in the system, it increases boiling point. A water with high pressure is going to take more heat to boil. It's going to take longer time to boil. That's what this means, okay? So the next is what? Dissolved substance raise boiling points. Dissolved substance raise boiling points. Low freezing point. When you have dissolved substances in the liquid, it raises the boiling point. That's why hard water takes longer to boil, okay? Because of the presence of dissolved substance in the water. So what are the effects of, what are the applications of increased pressure or decreased pressure in the system when boiling is involved as regards boiling? So what are the applications related to this? What? This effect of increasing or decreasing pressure. What are the applications? How is pressure applied in boiling? Let's find out. The first application here is in pressure cooker. It applies in refrigeration, okay, where you use high pressure in the condensers, okay, to aid in condensation of the cooling gas. All right, okay. It applies in distillation, in the making of distilled water, okay, high pressure during boiling. After boiling, you know distillation now, distilled water. After boiling water in a pot and you cover the pot, after 1 hour, 2 hours, come back to that pot, on the inner part of the lid of the pot. That water that hangs on the inner part of the lid of the pot, that's distilled water, okay? That water that evaporates, that's steam, condensed steam, that is distilled water, condensed steam. So ice, salt mixtures, and so on and so forth. Thermal expansion in solid. What is thermal expansion in solid? Thermal expansion in solid is broken down into various categories. The first category we have here is linear expansivity. And this is the symbol of linear expansivity. What is linear expansivity? It is the fractional increase in length per degree rise in temperature. So as the temperature increases, there is what? Increase in length, okay? There's increase in length of the substance as the temperature rises. That's linear expansivity, and it's directly proportional to temperature rise. That's why it's what? Linear expansivity. And the formula is giving us change in length is equal to linear expansivity length times change in what? Temperature. Check it out. This is the easy formula that you are going to use to solve questions that Jamb is going to set from linear expansivity, if any. So the next category we have under thermal expansion is what? Area expansivity, which is what? Beta. The symbol for linear expansivity is alpha, while the symbol for what? Area expansivity is beta. And what? Beta, which is area expansivity, is the fractional increase in area per degree rise. The fractional increase in area per what? Degree rise. But linear expansivity is the fractional increase in length per unit rise in temperature. Okay, but area expansivity here is the what? Fractional increase in what? Area. Okay, this one is length, this one is area. So the formula is given: change in what? Area is equal to what? Beta, which is our what? Our area expansivity times area times change in temperature. Chicken, as easy as that. So this formula is what you are going to use when Jamb asks you to solve for the area expansivity of a metal, of a body, and so on and so forth. Okay, volume expansivity, which is gamma. And what is volume expansivity? Is the fractional increase per volume per degree rise. Okay, the fractional increase per volume. Okay, so the first one we discussed, okay, linear expansivity, that one is what? The fractional increase per what? Per length. The second one, which is beta, which is what? Area expansivity, is the fractional increase in what? Area per unit what? Degree rise. Okay, then the third is what? Volume expansivity, which is what? The fractional increase in volume per degree rise. And the formula is given like so, which is change in volume is equal to what? Because this one is the increase in volume, that's why you have change in volume here. Is equal to what? The gamma, which is the volume expansivity, volume times what? Change in temperature. So everything here, when you substitute them, you are going to times them. Everything, you times them together. When you calculate change in temperature, you also calculate change in volume. You times all of these, then you divide both sides. As easy as that. Basic mathematics. What is the relationship between alpha, beta, and gamma? Let's look at the relationship. So if you want to relate them, we are going to relate them like so. Beta is equivalent to 2 alpha. Okay, so what does this mean? It means that beta, which is area expansivity, is equivalent to what? 2 alpha. Okay, so for example, in your question in Jamb UTME, you are given alpha, okay, and you are told to find what? Area expansivity. What are you going to do? You use this formula, the relationship. Okay, since beta, which is area expansivity, is equivalent to 2 alpha, what you have to do is just times your linear expansivity that they gave you, which is alpha, times it by 2, and you get your answer. You get your what? Your beta, which is area expansivity. Then y, which is gamma, volume expansivity, is equivalent to what? 3 alpha. So the same thing. Imagine your question in Jamb UTME. They gave you alpha, okay, which is what? Linear expansivity, and they told you to find what? Volume expansivity, which is gamma. What are you supposed to do? Since gamma is what? Is equivalent to what? 3 alpha. Just times what? Apply this formula, substitute, and times what? The alpha that was given to you by 3, and get your answer, Shikina. So you have to know all this. You have to be smart. You have to focus on what you need to know. Okay, let's go. So what are the effects and application of thermal expansion in solids? The application includes what? Railway lines. Okay, remember the effect of thermal expansion. Thermal expansion applies to railway line, and the effects. Okay, a metal that is used to make railway lines, it expands. Okay, when the temperature gets high, okay, the metal expands. Okay, that's why it doesn't easily break. Okay, it doesn't easily break, so it expands. Okay, as an adaptation to increase in temperature, which is the change in temperature. Okay, in bridges, it also applies to bridges, because bridges also what? Expand. Okay, when the temperature is high, so that the metal used to construct it will not get broken. Okay, it also applies to building strip, the same expansion. Okay, to prevent what? To prevent breakage. Another one is what? Bimetallic strip. Okay, in thermostats, like the one you have in your iron, your pressing iron at home, used to what? To control temperature. Okay, that bimetallic strip is used to control the temperature. This bimetallic strip controls the temperature. Don't look this bimetallic strip as a big word. Oh. It's not a big word. It's not a big jargon. It's not a big grammar. What is here is bimetallic strip. Bi means two. Metallic means metal. Strip means like ships. Okay, flat something. That's ship. Very flat and light. So it means 2 metallic flaps. Okay, 2 metallic flaps. Okay, one for what? High temperature, one for what? Low temperature. That's why it's called what? Thermostat. Okay, thermostat. It controls the temperature of the system, used in iron, used in refrigerator, used in AC, and so on and so forth. Thermal expansion in liquids. Thermal expansion in liquid, remember we just treated thermal expansion in solids. Now we are treating thermal expansion in liquids. Okay, the first category we have here is volume expansivity. And volume expansivity is defined as the increase in volume per degree rise in temperature. The increase in volume per degree rise in temperature. That's self-explanatory. Let's now compare real versus apparent what? Expansivity. Jamb says we should get accustomed to this. Okay, real versus apparent expansivity. What is real expansivity? Real expansivity is directly proportional or is equal to, is equivalent to actual expansion of liquid. Real expansivity is equal to the actual expansion of the liquid. So it's real, it is the actual expansion. Okay, so apparent expansivity is equal to observed expansion when liquid is in container. So what you see, since container also expand, you know that when liquid expand as a result of high temperature or secondary to high temperature, the container also expands because the container is metallic, so it expands too. When there's what expansion in liquid, volume expansivity, there's also thermal expansivity. Okay, so apparent expansivity is the one you observe, okay, when the liquid is in the container, okay, the one you observe. But real expansivity is the actual expansion of the liquid inside the container. Hope you got that. All right. So how do we determine expansion in liquid? How do we do that? How do we determine expansivity in liquid? We use what? Dilatometer. Dilator what? Meter. Don't forget this. Oh, dilatometer for your Jamb UTME. Let's go. Still under the thermal expansion in liquid. Okay. Anomalous expansion of water. Jamb says what? We should be accustomed to this. And what is anomalous expansion of water? When water contracts from 0 degrees Celsius to 4 degrees Celsius, then expand above 4 degrees Celsius. So water contracts from 0 degree to 4 degrees what? Celsius. Then what? Expand above that 4 degrees Celsius. Okay? It expands above that 4 degrees Celsius. And what is the application of this anomalous expansion of water? It's important for aquatic life survival in cold region. Exactly. All those organisms that are in water, okay, it's important for their survival. Because they need different temperature. Their temperature varies, okay? They need temperature maintenance to favor their life in the aquatic environment. Now that we have understood the concept of expansion of solid and liquid as a result of increased temperature or a change in temperature, let's quickly test our knowledge, the knowledge we've acquired so far, by taking some Jamb must repeat questions. Jamb must repeat questions. Question 52. A 2 kg block of copper is heated from 20 degrees Celsius to 70 degrees Celsius. If the specific heat capacity of copper is 400 joule per kilogram Kelvin, how much heat is absorbed? A. 20,000 joule. B. 40,000 joules. C. 50,000 joules. D. 60,000 joules. Drop the answer in the comment section. Question 53. How much heat is required to completely melt 0.5 kilogram of ice at 0 degrees Celsius? Take specific latent heat of fusion equal to 3.3 times 10 raised to the power 5 joule per kilogram. A. 1.65 times 10 raised to the power 5. B. 3.3 times 10 raised to the power 5. C. 6.6 times 10 raised to the power 5. D. 1.0 times 10 raised to the power 6. All options in joule. Drop the answer in the comment section. Question 54. Which of the following correctly distinguishes evaporation from boiling? Jamb regular customer. A. Evaporation occurs at the surface. Boiling occurs throughout the liquid. B. Evaporation occurs at boiling point. Boiling occurs below boiling point. C. Evaporation requires bubbles. Boiling does not. D. Evaporation is rapid. Boiling is slow. Drop the answer in the comment section. Question 55. A metal rod of length 1 meter expands by 0.001 meter when heated to 100 degrees Celsius. What is the linear expansivity? A. 1 times 10 raised to the power minus 5. B. 1 times 10 raised to the power minus 4. C. 1 times 10 raised to the power minus 3. D. 1 times 10 raised to the power minus 2. All options in Kelvin raised to the power minus 1. Drop answer in the comment section. Question 56. Which statement about water is correct? A. Water expands continuously as temperature decreases from 100 degrees Celsius to 0 degrees Celsius. B. Water contracts from 0 degrees Celsius to 4 degrees Celsius, then expands above 4 degrees Celsius. C. Water contracts continuously as temperature increases. D. Water expands continuously as temperature decreases from 4 degrees Celsius to 0 degrees Celsius. Drop the answer in the comment section.